So I want to finish the cubic spline interpolation analysis in this video. In the Part A video, then, we set up the problem. So we have these n+1 points, and we have these n piecewise cubic polynomials that we're using to interpolate those n+1 points. We require that the function go through the points, and we also require that this interpolating function will have a continuous first derivative and a continuous second derivative. When we did that, we came up with, we have these 4n unknown coefficients, and we came up with 4n minus 2 constraints on them. Those are given by these four formula. di equals yi, and then formula 2 and formula 3 and formula 4. We're still missing two constraints, but nevertheless, we can simplify these four formula and boil it down into a single formula for the b coefficients. You can see how to do that. We can start with this equation number 3 and solve for ai in terms of the b coefficients. And then we can move to equation number 2. So the ai are known in terms of the b's. We have the b's here. So we can solve equation 2 for ci in terms of the b's. So then we have the ai's in terms of the b's and the ci's in terms of the b's. The di's are already eliminated with equation 1. And then we can plug all of that into equation 4. And equation 4 then becomes an equation just for the b's. So we solve equation 3 for ai, 2 for ci, and 4 becomes an equation for the b's, which looks like 1/3 hi, which is known, times bi, plus 2/3 hi plus hi plus 1, which is known, times bi plus 1, plus 1/3 hi plus 1, which is known, times bi plus 2, is equal to a right-hand side eta I plus 1, which is known, over hi plus 1 minus eta I over hi. So this is a matrix equation for the b coefficients. Okay? There's a technicality here. In the original problem, there is no b sub n coefficients. The coefficients stop at index n minus 1. But I include a definition of b sub n. So then we'll have a b sub n in this equation. This one will then be is supposed to represent an n+1 by n+1 matrix equation for b0, b1 through bn. But we're missing two equations, right? We're missing two equations. We're missing two constraints. So that works out to be missing the first row of the matrix equation and the last row of the matrix equation. You can refer to my lecture notes to see what this matrix equation looks like and how I write it with the first row missing and the last row missing. So we need two more constraints. That's called the not condition. There are other ways of specifying the constraints, but this is the default in MATLAB, and it's the one that you would usually choose when you don't have any additional information. Not a not refers to the fact that these points on the graph that you know are called knots. So not a knot here, I can draw the graph to make it more clear. So if we have, say, it's only the first 2 points here, right? So I'll draw 3 points here. This is our x0, this is our x1, this is our x2, y1, y naught, sorry, y1, y2. We have our interpolating polynomial here. So it looks, say, something like this. These points are called knots historically. They're called knots because this type of interpolation was done with rope and nails on a board. So it was knots were the knots in the ropes. But this is, so then the words are still carried over. The not a knot condition is basically saying that these two interpolating polynomials are equal. So they're the same function. So this is g naught, this is g1. So the not a knot condition is saying that this function of x, g naught of x, is the same function as g1 of x. So this middle thing is not really a knot. In order to implement this, this is one condition. In order to implement this, basically all we need to do is require, we already have the function, the first derivative and the second derivatives are equal at x equals x1. So in order for these two functions to be equal, we actually only need to require that the third derivative at x1 is equal to the third derivative of g1 at x1. So this is equivalent. These two conditions are equivalent. Okay? And then also equivalent then if you take the third derivative of the interpolating polynomial, you would end up with a0 equal to a1. So also equivalent. Okay? So one more constraint saying that the not a knot condition applied to the first two cubic polynomials is a naught equal a1. That becomes the first equation in the matrix. The second constraint applies to the other end. The other end then would be, remember that there's n of these matrices. So it would be g sub n minus 2 of x equals g sub n of x, n minus 1 of x. So that's the right-hand side, the end of the interpolation. And that would, equivalent to the third derivative, that would work out to a sub n minus 2 equal to a sub n minus 1. Okay, so these are also equivalent. Okay? And that will give us two more equations for the b coefficients. So we add that to our matrix equation in the first row and the last row. You cannot solve this matrix analytically. So you use MATLAB to solve the matrix equation. It's a tri-diagonal matrix. You find the b coefficients. Once you have the b coefficients, you can then find the a coefficients and the c coefficients. The d coefficients you know. And then you have the interpolating polynomial. So you use that then to do interpolation. To code this up would take a long time, would be a complicated exercise. I've never done it. It's, I think I could do it, but I wouldn't want to. You just use the built-in functions provided by MATLAB. But it's useful to know then what the underlying software is doing, to learn about the not a knot condition, because you have, that's the default in MATLAB, but you can change the default. You can specify two other conditions. For instance, if you knew the derivative of the function at x naught and the derivative of the function at xn, then you can apply those two conditions instead of the not a knot condition. So let me summarize about cubic spline interpolation. The reason to use cubic spline interpolation is because you want a very smooth interpolating function through your, and that goes through your n plus 1 points. Sometimes it's very useful in an aesthetic sense. And sometimes it's just a very powerful way to interpolate functions more accurately. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.